This is a non-scientific way of figuring it out, but I think this will hold for most of them. It's generally the most complicated one is the function. If you just kind of because and generally the least complicated one is the second derivative. Right. So this is the function f, because if you look at it, if you draw the slopes on it, they're positive, positive. Here it's 0. So this one is positive, 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 0. This one's negative, negative, negative. So this one's positive, 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 0. And then still is positive, positive, positive like this one. So this is f prime. And then the constant one is going to be f double prime because it's, well, negative, 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 0. This one's negative, negative, negative slopes, 0. And positive slopes, and that's positive. So again, generally most complicated is the regular function. Same with this one. So this is going to be the actual function. Generally, I look for where it's 0. That's helpful. So this one where the slope is 0. So here the slope is 0. And you can see, well, the slopes of this one would have to be negative, right? Which this is negative. And then it's 0 there, same place. So that's 0, and then it's positive, and this one's positive. So it goes away. This is f. This is f prime. And then this is f double prime, because the slope of this one is constant the whole way, and that's a constant. So not a scientific way of figuring it out, but generally the most complicated one is the function. Don't quote me on that, but it's what it seems like to me. All right. Do you guys have any questions on these homework problems? I can put them up there, but did any of them seem particularly hard?
Yeah.
All right, this is 17. So we're going to find the second derivative on 17. So dy dx first. So view this not as, don't view that as a quotient rule. Did you view that as a quotient rule the first time? This is the same as 1/3.
I don't remember if I got it.
Okay. So it should be 1/3 e to the negative 3x times the derivative of the u. That's negative 3. So this is not a quotient rule because this is a constant, not a function. Plus 2e to the 2x times 2. So simplify that. This one and this one cancel. So it just becomes negative e to the negative 3x plus 4e to the 2x. That's the end of our first derivative. Simplify it. And then so b squared y x squared is then negative e to the negative 3x times negative 3 plus 4e to the 2x times 2. So then that becomes positive 3e to the negative 3x plus 8e to the 2x. So basically what happens is you just multiply this one by negative 3 twice, and you multiply that one by 2 twice. Because e to the x is e to the x, and then times the derivative of the u, the derivative of that is negative 3, the derivative of that is 2. So it ends up being just this, multiplied by negative 3 twice. If you multiply a third by negative 3 twice, you get positive 3. And then you multiply 2 by 2 twice, you get 8. I can pull up the answers, and then if you have more questions, I can do that. Solutions going over those. today what we're actually going to do is, just so you guys know, like, some more about logarithms, in case you were to need those properties at some point, we're actually going to flip back into the, it's like 0.8, or actually 0.7, sorry, on page 24, and just give you like a brief overview of log properties. Unit 0, which is the review unit. So 0.7, which again is page 24. So this is kind of a review over all logarithms, basically what logarithms are in log properties. So I thought it wouldn't hurt to do an overview of this today. Because I think nobody really learned that much about logarithms before, right? Okay. So it'd be good to just have at least an understanding of them. Here's the graphs of logarithms. Logarithms and exponentials are inverses. So yesterday, so like natural log, so I told you yesterday, is really log base e, just a shorthand way of writing log base e because it's a common one, and it's the inverse of e to the x. Those two are inverses right there. So log base e is the inverse of e to the x, in the same way that like log base 10 of x would be an inverse of 10 to the x. So those are inverses of each other. So they're kind of reflections. They reflect over the axis y equals x. It's really just most important that you know the fact that natural log and e's are inverses because they like undo each other. So here's some facts about the graphs. I wouldn't concern yourself too much about the graphs other than you do kind of need to know what the graph of natural log looks like. Know that natural log crosses at 0, 1. Sorry, 1, 0. That's going to be true for all logarithmic functions, and all exponential functions cross up here at 0, 1. And if you just think, why is that the case? Because any exponential with 0 as an exponent is just 1. So, in the same way that any logarithm evaluated at 1 is just going to be then 0. So it is important that you know that like the natural log of 1 equals 0. Important to have to know. All right. And here's some more facts about the graph, the domain and the range. Just know that there is like a vertical asymptote. So we're going to just sort of do this part. But the natural log, and I've drawn this a few times, goes through here, and there's a vertical asymptote there on the y-axis. Like I said, you can't plug negative numbers into a natural log. And so just a basic little property sketch. If you had to sketch the natural log of x minus 2, you guys remember what this x minus 2 does to it? When we learn transformations. What does it do if you have a minus 2 inside?
Shifts the
Yeah, just move to the right too. So remember, inside is left and right, and it's the opposite, and then outside is up and down. So it's the same. So this would be right 2. So if you were asked to graph the natural log of x minus 2, all you would do then is the parent function natural log goes like this, right? Goes at 1, 0. So then x minus 2, you would just move that one point that you know there over 2 spots. It would also move the asymptote from 0, move it over 2 spots. So now it's asymptote's at 2. And then it would just be the same, so crossing that 3, 0 instead of 1, 0. So an easy graph. The main thing that you might need to know though is some of these properties here, how to change from logarithmic to exponential form and vice versa. So this is kind of the main definition here. I always learned it with B's, but here it uses A's instead of B's. It's not really a big deal. But basically, you can change something from a logarithmic form to an exponential form pretty easily. And we'll do a couple practice problems doing that. But if you have something say like log base, sure log base 2, 25. Let's do log base 5. Trying to do the inversion. All right. So let's say you were asked to find what is log base 5 of 25. Probably have no idea, right? What?
2.
Yeah, it's 2. Yeah, so it's actually pretty easy. And how you get that is using this property right here. So you can rearrange this and notice how this, you can write this in exponential form. You take the little base there, 5, to the, and this would be our y out here, our answer, right? So y. So you write 5 to the y equals the big number 25. Okay. So then you just think, well, 5 to what power is 25? It's 2. So log base 5 of 25 is 2. Using exponential values. And you can go the opposite way. So then, like for example, this one would be log base 3 of 81 equals 4. So that would be going the opposite. Because then 3 to the 4th equals 81. So in the same way, this one, log base e of 1 equals 0. You don't have to use these extensively in calculus, but I just want to make sure you've at least seen them before. Now C, look, that one doesn't have a base, and remember what the base is if it doesn't have one?
10.
So there's an invisible 10 here. We just use the log for log base 10. So this would be 10 to the negative 1 equals 0.1. And that's true. All those are true. 10 to the negative 1 would be 1/10, right? Right. So then some other properties here. E to the 0 equals 1. So then the natural log of e, so let's see, I'm sure it's 1 equals 0. I'm sure what it's trying to do. Oh, this one's e. Natural log of 1 is e. I'm not sure what it's trying to get you to do there. I'm not sure what it's asking you in that one. But I think it's just getting you to take the, okay, yeah. So it's kind of confusing, no one will get it, but since we know that e's and natural logs are inverses of each other, often, so like if you were asked to find like e to the x plus 2 equals 5, if you were asked to solve an equation like that, you guys know how you would solve that? Okay, so how you would do this is you use the fact that e's and natural logs are inverses of each other, and what you would do is you take the natural log of both sides. So in the same way it was like dividing on both sides and multiplying on both sides. You take the natural log of both sides, and the natural log of e cancels. So it leaves you with just x plus 2 equals the natural log of 5. Natural log of 5 is just a number, it's just a constant. And then so x would be natural log of 5 minus 2. And again, that's just a decimal. Natural log of 5 is just 1 point something. So using the fact that those are inverses, here the natural log of e to the 0 equals the natural log of 1. And then so that the natural log of e cancels, so 0 equals the natural log of 1. So that's what it's trying to do. So let's do drop down here. Use this inverse idea to simplify some of these. So what would be the natural log of e to the radical 2?
Just down to 2.
Yep, and just cancel. Okay, and e to the natural log of 3x would be just 3x. And the same can be said for other exponentials with the same base. Because remember, this natural log is actually e to the log base e of 3x. So e to the log base e cancel. That's why they cancel. So on this one, this is really 10 to the log base 10 of 2. So the same thing is true. 10 to the log base 10 cancels, so we're left with 2. This is log base 2 of 2, so those cancel. So the main thing to get out of this is logarithms and exponentials are inverses, so if you do an e or an exponential to the log, they cancel, or a log of an exponential, they cancel. That's the big takeaway. And mostly, I would say you're only going to be asked to use this property that e's and natural logs are inverses of each other. This is less rare. Okay, and there's one other thing we need to say about natural or logarithms in general, is these special properties that they have, and that is I showed you a little bit of this yesterday. These first two rules, and that is that you can split natural logs apart, and you can bring them back together as long as they have the same base. If two things are multiplied, you can split them up using addition, and if they were added with the same base, you can bring them together using multiplication. Same with division. If two numbers are being divided in a logarithm, you can separate them using subtraction, or if they were being subtracted, you can bring them together using division. One that we didn't see yesterday was this one here, whereas that if you have something raised to a power, you're actually allowed to bring that power down in front of the logarithm. That can come down to the front. And we'll look at a couple examples of these. So first one, the natural log of 5/8. So we're just going to expand this using this property here. So this would just be the natural log of 5 minus the natural log of 8. You just split it up right using the same base. This next one's a bit more complicated. So we got this cube root here. What we actually want to do is view this as the natural log of x squared plus 1 raised to the 1/3 power. Okay. And then we use this fact here for the natural log of a to the n. You're allowed to bring that down in front. So this becomes 1/3 times the natural log of x squared plus 1. that's actually all you can do with that one. You might think, well, can you split that up or whatever? You can't split this up. You can split it up if it was multiplied. You could split it into the sum, but this one's a sum inside of it. And these next few, we're supposed to condense these into a single logarithm. So let's see if we can do that. The first one, the first thing you want to do is take these numbers in front and do the opposite of the rule we just used and put them up there as powers. So those go up in the top. So that becomes the natural log of x to the negative 3 plus the natural log of y to the 5th. Now this is a sum of natural logs. They have the same base, so we're allowed to bring them together. It's addition, so it will become multiplication. So this will be the natural log of x to the negative 3rd, y to the 5th. Okay, and we do the same for the next one there. And then when you combine these, when you have a series of plus and minuses, basically you just think of like the plus ones being in the top of the fraction and the minus ones will be at the bottom of the fraction. So this becomes natural log of x to the 1/2 times x plus 1. And then the bottom, since this is minus, it would become y to the bottom. Just think of pluses being in the top, bottoms in the, or negatives in the bottom. More to solve. All right. This example A here, it's supposed to solve for x, but I don't think you can actually solve for this except for in terms of y. So we're just supposed to get the x by itself. This might actually help with implicit differentiation, which we're going to do next. So if we're to get the x by itself, what do you think we would do here? Okay, so we'll do that, but I want to move the 6 over first. So just to show you why here, if I move the 6 over first, then we can get sort of like direct access to that. Whereas if I did the natural log on both sides to begin with, I'd have the natural log of e to the 2x minus 5 plus 6. All of that inside of there, so I couldn't just like split. Does that make sense?
Mm-hmm.
So move that over, and then yeah, we want to do natural logs. So anytime you see an x and an exponent with the e, you're going to be doing a natural log. So now we'll natural log both sides. And so we get the natural log of y minus 6 equals 2x minus 5. and then getting x by itself, we would add the 5 and then divide by 2. Just that one step. Natural log of y minus 6 plus 5. That works. And maybe think about what we could do with this next one. What would you want to do first on that one?
Combine.
Yeah, we'll combine them because they do have the same log base. It's a minus, so that means it's going to be division. Right? Log 2 x over x and z. So it's 3. Now, any ideas after that? So think logarithmic to exponential form. So like what we did here. Here, sorry. This. So we're going to do 2 to the what? 2 to the third equals x over x minus 3. So let's change it from logarithmic to exponential. That makes sense by then?
Yeah.
And it's hard to see if we haven't done these. It's done a lot. And then we get 8 equals x over x minus 8. And I should be able to solve this one. You can then multiply both sides of x minus 8. So we get 8x minus 64 equals x. So then subtract that one, add it. 7x equals 64. X is 64. 7. And there's one other log property. I know it's kind of a lot, just kind of a flyover of all these log properties. Called the change of base formula. And I think I mentioned this yesterday as well, where you can basically solve any of these logarithms just using like the log button or the natural log button on your calculator. So the change of base formula says if you're asked to find log base 7 of 112, well, you can actually just do log, it works for log or natural log. You can do log 112 divided by log 7. Or you can do natural log 112 divided by natural log 7. This would change the base formula. Either way you do it, if you try it on your calculator, log 112 divided by log 7, 2.424. And you can do the same thing, natural log 112. Natural log 7. We got 6. Find an exact value for x if 3 to the x plus 2 equals 6. Anybody know how to do this? So if this was an e, say this was e to the x plus 2, what would you do?
Translate,
Right. So use that same strategy. Instead of canceling with the natural log, cancel with log base 3. So if you did a log 3 of both sides, log 3 of 3 to the x plus 2, and log 3 of 6, that will cancel out to 3. So that's how you move from the x. And then we subtract the 2 over x is log 3, 6. And then we can get an exact answer using our calculator. The next part, we can just do x is, I just said a natural log of 6 over the natural log of 3 minus 2, using the change of base method. And you got like negative 0.369. So, and like a traditional pre-calculus class, you would probably take like a week and learn all those problems. You guys are smart, so probably can get it in a day. It's kind of what you gotta do. I don't want to do all of these problems. That would be too much. But I was thinking maybe we could do maybe you could do like all of like either the evens or all of the odds. I don't really want you to do the sketches though. Okay. So we're doing either the evens or the odds.
Whichever one would be easier and take us up.
Probably, I don't know. I would say probably the odds because the evens they always generally give you like end with the hardest one, and that's like there's an even that ends all the sections. So probably the odds.
Then let's do the odds.
All right, do the odds.
So the odds are in your favor.
Yeah.
The
So-
odds are never in my favor.
So we'll do the odds. I'll give you a lot of problems. All right, we'll do some of them together. And I want to do the sketching. Too much work. Okay. Yeah. All right. So let's try the odds from this section. Let's make sure you got a few of them done. Okay. So decide whether these are true or false. So let's see. Is this true? Number one.
No.
Okay. These are probably wrong. False. 3. True or false? True. Okay. So this is written a little bit different. It's not true. It would be true if it was log of A over B.
I thought that was it.
Yeah.
Something felt wrong about having logarithm.
They kind of like combine the change of base sort of with that, yeah. So it's pretty controlled wrong, that's all. What about 5?
True.
That's true. What do you think?
I think it's true.
Alright, wrong again.
Oh my god.
Goddamn good.
It's if it was the natural log of x cubed, then you can bring it down to 5.
Oh, it's not.
Oh.
False. This is pretty tricky. I haven't looked at this yet. Alright, so what do you think 7? I just kind of gave this one away.
If that one's not true, then I'm literally
This one
walking
is
out.
true because it's just the property of the addition. Okay. That was fun.
That was fun? Oh.
Alright, exponential to logarithmic or vice versa. Okay. So I think it's easier, for whatever reason, for me, it's easier to go from logarithmic to exponential than the opposite. So I want to look at number 11 first. I guess it's easier to just see the numbers. On number 11, how would we write that to exponential?
Um, 3 to the 6.
Yeah. So, because typically that's what you're going to do. You don't normally want to take something from exponential back to logarithmic form, because exponential form is generally how you're going to solve it. So this to me makes a lot more sense to go from here to here, but nonetheless, you do have to know how to do the opposite, really, I guess, at least for this part. So now think in reverse. This 3 was the base, so then that log, it's going to be a log of, the big number becomes the base, so the big number here is 5, that becomes the base. And then the little number up here is the y, so that's the equals part, right? So this would equals -3. And then the number on the other side is the big number. I would say you don't really need to know how to do that. I mean, don't, like, that's how it works. And then you can always check it. 5 to the -3 does equal 1 over the top. All right, 13. What happens here?
Potential
Yeah.
times 2x.
Yep. These and natural logs cancel. 15 log 5 of 5. What happens there? Yeah. So it just gets rid of. Alright. 17. What do we do here? So think logarithmic to exponential form. Yep. The variable x. X is what? Yeah. Ooh, 19 is a little bit more challenging. What do you guys do first? Remember I said like exponential form is generally always easier, right? So let's take that to exponential. Three to the x squared minus 1 equals 27. So it's always the base becomes the new big number. The other side becomes the exponent, and then that big number goes to the other side. So we're still not out of the woods yet, though. This is actually a property we haven't seen yet. So you could do log base 3 if you wanted to, right? Log base 3 on both sides. There's actually another property that we haven't seen, but if you can write two things as the same base, then what do you think would be true of your exponents? It'd have to be the same, right? So is there a way that we can write 27 as 3 to the power? 3 to the power is 27. Mm-hmm. Doesn't have an example like this. So when you do that, by writing them with the same base, you can then just set the exponents equal to each other. And part of the reason why is because then you're essentially just taking the log base 3 of both sides. You don't need to write that because it just, in mathematical sense, if you have the same base, the exponent is going to equal. So x squared minus 1 equals 3. So I'm kind of doing that, but without doing it. So the next squared is 4. So the x is plus or minus 2.
What is with the plus and minus?
But you actually, in this one, I'll do both because you're gonna square it. Well, there's certain situations where you want plus or minus, and certain situations where you don't want plus or minus. And it is confusing. You do in this one because if you plug them back in, you're going to get the same answer for both, right? If you put positive 2 in, you get 3. Negative 2 in, you get 3. But if you were, it just depends on the situation. So we can skip that. So you guys just got to do the rest of that 29. So this is going to be expanding, condensing, try to solve just that one without a calculator. That should be doable. With calculator, and change the base. All right, so not much more.